So, first ionization energy is how much energy it takes. And Allie, you might want to turn some of the lights off. I don't know. Whatever makes it better for you guys. Energy that it's going to take to remove an electron from the gas from a neutral atom in its ground state. So the stuff has to be in a gas form before they can actually do this. This is pretty much probably the last time you really need to concern yourself with the fact that it's a gas state, but just realize that that's part of it. So the first ionization energy is going to decrease as you move down a group, and we're going to talk about why here coming up, okay? And it's going to increase as you move across the periodic table, okay? So let's talk about why. Is that on the next slide? Let me just click here. Okay, here we go. All right, so it's as we move across the periodic table, it's going to increase because you're adding in more protons as you move across. So as you move across, you're adding in more positive charges, but that distance to that outer electron isn't changing much. Because as we move across, we're still in the same level, right? Does that make sense? So your distance hasn't changed much, but the number of magnets or protons pulling on that electron has. So it's going to take more energy to pull that electron away. Does that make sense? Okay. Did I skip going down? No, we need to talk about going down. As we move down the periodic table, we're increasing what? Levels. So therefore, if we go back to our Coulomb's law, we're increasing the distance. The further the thing is away, the easier it is to pull. And I've often made this analogous to like when you were a baby, right? When you're a baby, your mom is like holding on to you tight, like nobody's getting you. And then you get into your toddler stage and she's holding you by the hand. It's a little bit easier to pull you away from mom, right? And then you go off to kindergarten. So mom's not there with you all the time, but she's got her eye on you, or somebody does, right? So it's still pretty hard for you to get into mischief. Then you get into middle school, and then you get into high school, and now you're driving, okay? A little bit easier for you to get into mischief, yes? Compared to when she was holding you like this, okay? The further you get away from the nucleus, the easier it is to pull those electrons away. You can think of it as Shrek. It's layers of the onion, right? Shrek, they talked about the onion. Okay, yeah. All right. So as we move down, it's easier. So francium is going to have one of the lowest first ionization energies because it's the furthest away. And from the nucleus, right, out, you've got that distance there. So it's going to be easy. And then your effective nuclear charge for francium versus 118, which is out there now, which is OG, original gang stuff, right? OG, it's going to be much greater for OG holding on to that because it's got a much more higher effective nuclear charge. More protons are there versus this one. Helium then is going to have the highest first ionization energy. Closest and higher effective nuclear charge versus this guy. I'm taking my 5-minute mass break. Oh, Lord. There we go. Okay, so does that make the idea of first ionization energy make sense? All right, now there are a couple exceptions. Okay, here's your hydrogen, here's your helium. Then from helium we drop way down to lithium. Why is there the big drop here? Second level. What in terms of Coulomb's law? Greater distance, right? and then it goes up, and then it kicks back down just a little bit. Why? Layers of the onion. S, 1s, 2s, 2p's just a little bit further out, isn't it? So our distance increased just a scotch.
Why?
1s, 2s, 2p. So 1s, here's your 2s, your 2p is like right here. They're still very close together, but it's just a scunch, a little bit further out. Okay, distance increased. Then we climb, climb, climb. Here we're at 2p3. What happens here? Why? Not more distance. They're still in the p. They're still in the p thing here. Think about your electron orbital diagrams. Exactly. Here is where we double up. Okay? So you're in a 3-seat car. At this point, you've got somebody sitting on somebody's seat or somebody's lap. Okay? You get in a car accident, they're going out the windshield first, right? Okay? Same idea here. You're doubled up, you've got that repulsive force. So in terms of Coulomb's law, now instead of attractive forces, you've also got a repulsive force there too. That electron's kicking that other electron out. Does that make sense? Okay? So all goes back to Coulomb's law. And you can see go, 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 go up, and then we kick way back down again. Why are we kicking down here for sodium? Distance increases. Then we go up, we kick back down. Why? Distance increases. Here, we're kicking down just ever so slightly. Why? Repulsive force, we doubled up. Okay? Increase distance, increase our effective nuclear charge up to our noble gas, and then we increase our distance, we plummet back down again. Okay? Thumbs up. Make it in terms of Coulomb's law. Make it in terms of effective nuclear charge. Okay? They love those words. They get really excited when they see that. All right, we can also have second ionization energies. This is for removing another electron. So now you've removed one, now you're going to remove another one on top of it. We can look at these successive ionization energies. So we can keep removing and keep removing and keep removing until we see this large jump in ionization energies. And where we see that jump, that means that we've kicked back another level because it's gotten closer to the nucleus, significantly closer, which means that we've gone up a level. Okay, so here, if you look at this in terms of where this is really showing a dramatic increase, you can see it showing between here and here. See how huge that increase is there? That means that after they removed this second electron, this guy, whatever he is a noble gas. Where that big jump happens, that indicates that you're at a noble gas. So if I go back 1, 2, 3, 4, 5, 6, 7, 8, you see how this gets huge again, like massively huge? Oh, mass breaks over. Massively huge. That means that this guy is going to be a noble gas because it's going to be really hard to pull that electron away from one of those noble gases. This is a very common question that you will see on the AP exam. I would be surprised if you don't go through an AP exam that you don't see some sort of variation of this on there. And Austin is shaking his head in confirmation. Okay? Very common. So look for the big jump. Where the big jump happens, that is your noble gas. Because it's going to be really hard. Remember, the effective nuclear charge of that noble gas is very high compared to the previous thing that it was. Okay? All right? Everybody cool? All right. Next one is atomic radius. There is a difference between atomic radius and ionic radius. Okay? We'll get into the differences here coming up, but this is atomic. So this is the atom without any electrons added or removed. Okay? As we move down the periodic table, why does it get bigger? You're adding more layers. It's the onion, right? Sometimes I'll talk about this in terms of like clothing. Okay, during the summer, you're walking around in your bathing suit, but by the time, January hits, you've got so many layers on, you're walking around like Randy from Christmas Story. Yeah? Huh? I know, I love that one. I can't get up, help me, Ralphie. Okay, so that explains going down. That makes complete sense, right? Everybody's cool with that one? It's the going across that people have more trouble with. Okay? So think of this as your magnets, right? The first column, you've got like one magnet there. Okay? Same shells out here, but you've got one magnet in it. Then we're adding another magnet, so we're pulling it in tighter. Then we're going to add another magnet in, and another magnet, and another magnet. So by the time you get across here, you've added in 8 more magnets. You're pulling that in tighter. But then you kick back down here, and now you've added another layer. Sir?
The only way that I found was kind of easier to think about it is, like, as you're going across, you're adding more protons and electrons, but the protons are so much more, like, that's where we get our atomic number from, or our atomic mass. So the protons are going to have a much more significant effect than the electrons are telling them, so they're going to bring them in more and more.
Okay, so whatever way you've got to remember that, but just remember that as you move across, it gets tighter. Okay, so those protons are pulling tighter and tighter. You're not adding in extra layers, but you're adding in extra protons in the middle to pull it in. The layer's still the same. Yeah, you're adding in an extra electron, but the layer's still the same. All right, so that's that trend. And then I think you get the idea here. Again, the effective nuclear charge is going to increase. We talked about that. All right. What is an ion? Okay, it has less or more. Both. I mean, both are an ion. A cation has them removed, so they have a positive charge. Cation, No, that's okay. Positive charge. And then our anions are going to have a negative charge. And I told you to remember there's like an antagonist in an English kind of class. Antagonists are always kind of negative people, right? So those, we've added electrons in. Okay? So for ionic radii, it's going to vary based on whether you're talking about cations or anions. Okay, and this you need to look especially at that effective nuclear charge. Okay, so if lithium loses 1 electron, okay, it has 3 protons pulling in, but it only has 2 electrons out here. So 3 pulling on 2, it's going to pull it in tighter than what lithium would normally look like. Does that make sense? A 3 versus 2. Lithium has 3 positives here. It had 3 negatives, but it lost that outer one, So now it just has these two. So the 3 are able to pull it in tighter. Good. Beryllium has 4 here. Okay. It's lost 2, it's 2 outer ones. So it has 2 here, but it has 4 pulling on 2. So it's going to be even tighter than the lithium would have been. It had 3 pulling on 2. Good. So that's why these are tinier, even though they have the same electron configuration. This guy is going to be smaller than this guy. Make sense? Okay. Going over here, I want to compare sodium now and fluorine. Okay. If sodium loses an electron, it's got 11 positives here. So I'm going to do my 11. I don't know how you want me to do 11. It's got 11 positives here. Okay. It's lost its outer electron. So how many electrons does it have? 10. So it's going to pull that in tighter, right, than it would have normally. Okay. But it has 10 electrons. Now I'm going to be neon. Neon has 10, it has 10, it's going to be like right here. Okay, good. All right, fluorine is going to be 9, but it's going to pick up an extra electron. So now I've got 9 pulling on 10 electrons. That 10 electrons are going to be able to get away a little bit further, right? Because it doesn't have as much positive charge pulling on that. So this fluorine will actually be a little bit bigger than it normally would have been. Oxygen's going to be even bigger because it's only got 8 pulling on those 10. And nitrogen's going to be even bigger than that because it's got 7 pulling on those 10. So think of it in terms of those things. Yeah.
Okay, so my question is, how do you know how many it's going to add? Like how many electrons it's going to add?
Oh, to become or get add or subtract?
Yeah.
So ultimately, and I'm going to personify the heck out of this thing, okay? Ultimately, these elements want to be noble gases, okay? So if you are in fluorine's column, if it adds 1 electron, it's going to look like a noble gas, correct? If it adds an electron, what charge will it have? Add electrons or what charge?
Oh, okay.
Negative. So it's going to have a -1 charge. Okay? Oxygen, to look like that noble gas, needs to do what? Add 2 electrons. And then it'll look like a noble gas. It's going to have a -2 charge. Nitrogen wants to add 3 electrons to get over there. So it's going to have a -3 charge. The carbon and those guys, they like to share more. They're all about sharing and caring. Okay? Then we get over to here. Your boron, aluminum, those guys, it's going to be easier for them to lose 3 electrons. If they lose 3, then they hop back to the previous noble gas. They're going to have a +3 charge because they lost electrons. Beryllium's column is going to have a +2 because if they lose 2 electrons, they look like the previous noble gas. And then the first column is going to have a +1 charge. Again, if they lose 1 electron, they look like a noble gas. Everything wants to be a noble gas. That is its goal because it's satisfied with that filled octet. Make sense? Everybody cool with all that? Remember all that stuff? Cobwebs, so many cobwebs we're dusting off. All right. Electron affinity, then, is the amount of energy involved when an electron is accepted by a gaseous atom to form a negative ion. The neutral atom's likelihood of gaining an electron. So the values tend to be negative to show that the energy is released as electrons that are added to the atoms. So as we go across here, it's going to increase in electron affinity. These guys over here want to add electrons. If they add electrons, okay, so this is how badly they want electrons, and fluorine wants it the worst, okay? That these arrows really should not include the noble gases because they're already filled, okay? So kind of visualize that as that arrow is ending here and ending here. It really should, okay? Fluorine wants it the worst. Francium is like, no, you take my electron, I don't want it, like just, it's yours, okay? Because if francium can give up its electron, one electron, it looks like radon. And that's pretty easy. Give up one electron, hey, I'm a noble gas, right? Okay? And fluorine's like, oh my gosh, if I just had one more electron, if I just did, then I would look like neon. And that's really what I want. Yeah, you guys are going to be in the AP exam going, if I just had one more electron. No?
One more.
Just one more. Just one more. Okay, so that makes sense. Here's your electron affinities kind of moving up and down. You can see, like I said, fluorine. Chlorine really wants it bad too. Bromine. All of these are your halogens. Okay, so you can kind of see that trend there. Electronegativity. Oh, they love electronegativity. Electronegativity is so important. Okay. Remember, electronegativity determines essentially what type of bonds you're going to form. We did some math last year or the year before and talked about that. And there's kind of a sweet number in terms of that we'll get into in the next couple chapters or units. Electronegativity also determines the order that you put your elements in when you write them in a formula. The least electronegative element is listed first. So like for sodium chloride, like I'm talking about in honors chem right now, your way over by the flag, your least electronegative element is listed first. Okay, so that's also another thing that we use our electronegativity values for. There'll be a few other things. We're going to come back to electronegativity in this course a lot. Okay, so understanding that trend is really important. It's a measure of an ability of an atom to attract shared electrons. It's going to decrease as you move down because you're getting further from the nucleus. So drawing those electrons in, that positive value, drawing those electrons in from the nucleus, it's not going to have as much pull anymore. Just like now that my kids have moved out of the house, I don't have a lot of control over them. Okay? I have more control over Benjamin because I'm still paying tuition and stuff for him. So I got a little control over him. But like I haven't seen him in a couple weeks, you know? Alex, he's out on his own. He owns his own house. Like I got nothing. Like he wants to move away and never speak to me again. Like I got no ties, you know? So the further you are away from that nucleus, the harder it is to kind of control that or grab onto those electrons. Okay? So they're not attracting them. As you move across the periodic table, your effective nuclear charge is increasing, and therefore, fluorine is the most electronegative element. They actually developed a chart with these, and everything is based off of fluorine. Fluorine has a value they assigned as 4. Okay? This is 3.5, 3, 2.5, 2. Hydrogen is 2.1. Everything else, if you remember those, if you remember this is 4 and then it just steps down by 1/2 each one, everything else goes down from there. So like this is like 3. Like that was 4, so 3.7, 3.8, something like that. And it just keeps stepping down. It's the trend you need to know. You don't need to memorize the values per se. It's the trend you need to be aware of. Okay? So if we want to try to figure out like our bonding, for example, we're going to go back to electronegativity to do that. So if we have two elements that are the same, so for example, hydrogen and hydrogen, it doesn't matter what their values are because the difference between them is going to be what? 0. Okay? Now for hydrogen, it's 2.1. So 2.1 minus 2.1, 0. Okay? No difference. Everything shared equally. You have a nonpolar covalent bond. Oh, remember these words. HBr, H is here, Br is way over here. There's not a huge difference in those. I'd have to look up the value for Br, but it's not a huge difference. There's some, you're going to have a polar covalent, and we'll actually get into the values for these. And I'll have you memorize a few of these, not many. And then a very large difference in those electronegativities, you're going to have ionic. The best way to remember between ionic covalent is if you have something from this side and something from this side, it's ionic. If everything is from this side or it has hydrogen in it, it's covalent. If you think of hydrogen as, because hydrogen is a nonmetal, right? Nonmetal and nonmetal is covalent. Metal and nonmetal is ionic. That's the best way to remember it. All right, so here you go. For the following pairs of elements, choose the one with the highest first ionization energy, largest atomic radius, and highest electronegativity. Go. Talk to the person next to you if you need to. Okay, I'll run the quiz off. I gotta write your quiz for tomorrow too. You guys are excited to have your first quiz tomorrow, aren't you?
Yeah.
Which one? Feel it. I have a poor child adding into my class today.
Ooh.
Not this hour, 6th
Oh.
hour.
What? Yeah.
All right. Yes, sir. Yeah, what? What do you say?
I just have a quick question.
Oh, yeah. And are we almost done with time?
I don't know. I can't remember the time.
Oh, okay. I'm fine then. What was your question, Matthew?
Why has the noble gases left behind so much energy?
Electronegativity, because they don't want electrons. Remember, electronegativity is how much the ability to attract shared electrons. I would have to, let me look it up and see. There's a table out here. Anything that we've covered so far? Yeah. Okay, so here's electronegativity. So here's your BR. We talked about that. So that would have been a 0.7 for the difference between those. Noble gases, these don't have any. When you get down to krypton, xenon, and radon, they start to have some. We will talk about how we talked in regular or pre-AP chem about how they have expanded octets. when you get down into these, and they can actually bond. It's somewhat rare, but it exists. So, but then you can see here that there are no electronegativity values for these. Yeah.
So if it's supposed to compare like Ne and like F for electronegativity,
Ne and F
yeah.
for electronegativity? Did they ask you that on your?
No, but like if it was an example.
They wouldn't.
Oh.
I wouldn't see that they would. I mean, I guess you would say that this has no zero. So this would have a much greater versus this. Because this has a filled valence shell, it's not going to want any electrons.
Yeah.
Okay. Now, like I said, these guys can have these expanded octets. That'll get into next. We'll talk about that more when we get into next unit. Okay. So when we're looking at higher first ionization energy here, sodium and lithium. So we're doing sodium, lithium, and fluorine and oxygen, right? Sodium and lithium and they wanted to know, what was it? Ionization energy?
Yeah.
So sodium and lithium, when we look at ionization energies here, ionization energy, sodium is here, lithium is here. This has a greater or a smaller distance between it. So this is going to have a higher first ionization energy versus sodium. And then what was the other one? Oxygen and fluorine?
Yeah.
Okay. This has a higher effective nuclear charge than oxygen does. So because of that, fluorine is going to have a higher first ionization energy. Good? Okay. Trying to see where I'm at here. Okay, there we go. I can switch between those. That's easier. Okay, atomic radius. If we're talking about sodium and lithium, sodium is going to have a higher atomic radius than lithium. So when we're talking atomic radius, that's this guy, because it has more layers. Okay, so it has more valence shells. I mean, you don't say layers on the AP exam. Like, actually say what it is. But I'm trying to get you to think in terms of like things that makes rational sense in your brain. Use the scientific terminology on the AP exam, though. Okay, so don't talk about onions and onions having layers. Talk about valence shells. Okay. So sodium has more valence shells than lithium. And then they asked about, what was the other one that they asked about? Fluorine and oxygen. Fluorine's going to have a higher effective nuclear charge than oxygen, but the same number of valence shells. So fluorine will have a smaller atomic radius versus oxygen. Then we talked in terms of electronegativity. Fluorine, I'm sorry, we were looking at these two. So electronegativity, sodium is going to have a smaller electronegativity than lithium. Why? It's further away from the nucleus. The outer electron is further away from the nucleus. So it's going to have a smaller than this one. And then we were looking at oxygen and fluorine. Fluorine has a higher, what's the buzzwords? Higher effective nuclear charge versus oxygen. All right, and then they wanted us to look at electronegativity. No, they wanted, did I cover everything? Yeah, that's everything on that one. And then this one was ranked from the, this is atomic and ionic radius. So you've got these three things, smallest, which one's the smallest to which one's the largest? Huh? Yeah, why not? We got time. Well, this is going to be atomic ionic radius here, and then the rest of these are just going to be atomic radius. You're comparing these three things to each other. Okay, so here you're going to be doing atomic and ionic radius, but then the rest of these is just atomic radius because you're comparing each one to the other. I think I am just going to draw on this guy. It's going to be easier to explain it to you guys. I think if I draw, I still got time. I still got time. That is the saddest looking circle. Need more time? All right. So this first one, this is the drawing for sodium +1 because it has lost an electron. It has 11 protons here, and it only has 10 electrons. So, and it's got one less layer, essentially, okay? One less valence shell. So that's going to be the smallest. Then if I go to sodium, now I'm still going to keep the same number of electrons or protons, but now I'm adding another layer, another valence shell. 11 protons, 11 electrons. So you can see the difference between these very quickly. This would be the smallest. This would be next. And then if I added one more electron, it's going to get even bigger because now I've got 12 electrons and only 11 protons. So it's going to get further out. Make sense? Okay. All right. Carbon, oxygen, and nitrogen. One, two, three, four. Ah, shoot. I got carried away. All right, so here I've got my carbon, right? Carbon's here. I got my 4 electrons out here. I got 6 positives in here, pulling on 4. Nitrogen, if I have nitrogen now, I'm going to have 7 positives, pulling on 5, but the distance, I didn't add any more layers here. Okay? So it's going to get smaller yet. And then oxygen, I'm going to have 8 pulling on this with 1 more electron. I've got 8 positives pulling on that, but I really didn't add much more of a distance. So ranking these, this would be oxygen, nitrogen, carbon. Jaden, you okay, honey? Okay. That is a pathetic drawing. Y'all, I do not draw well, and especially on this tablet. All right, next one. If we talk in terms of argon, we're going to have, how many positives? Argons, I got 18, okay? So argon, I've got 18 positives here. Don't start packing up on me. I got 2 here. I've got 8 here, and I've got 18 here, okay? If I change this now to chlorine, and I'm not changing it to chlorine ion, just a chlorine atom, okay? If I change this to chlorine, Now I only have 17 positives. I have 17 negatives, but I only have 17 positives pulling on that. So chlorine's going to be bigger. Argon's going to be smaller than chlorine, but potassium, I'm kicking down. You guys are packing up on me.
I haven't packed up yet.
This is 1. Look at you, goody two-shoes.
I know.
That's 19. But this is much further out, so the distance is going to be greater. So ARCLK. Right? You're not going to listen to me anyway. All right. So if you want to listen to the last one, go on and watch the video. You can listen to the last one on the video by clicking on that QR code. And I will see you tomorrow. Be ready for your quiz. And you finish 1-7. Finish 1-7 tomorrow.
Is it a quiz or a prize?
It is a quiz.
Is it a big quiz or a small quiz?
I have not written it yet, Matthew.
I'll write the answer. I will accompany you.
I think I looked at the table.
We'll accompany you on.
I found one at a back table the other day. There's extra copies in the bottom of that thing on the side here. It's the very bottom one.
Sorry. No, you're good.